Hello everyone, welcome back. In the last video, we were able to solve the tangent line problem by defining the derivative of a function at a point A to calculate the slope of the tangent line. So now let's suppose we wanted to find the slopes of the tangent lines at different points along the curve y equals f of x. For example, suppose we wanted to find f prime of 1, or f prime of 3, or f prime of -1. To do this, we would need to perform 3 separate limit calculations in order to find the slopes of the tangent lines at these different points. Now, as you can imagine, this can get quite repetitive and tedious to do the calculations. And so how can we simplify all of our work? Well, what we could do is define the derivative as a function, and we can use this function to calculate the slopes of the tangent lines at various points. So in the definition of the derivative, if we were to replace a with the variable x, then we get what is called the derivative of f. So we can define the derivative as a function rather than the derivative at a point. Now there are many notations that you might come across for the derivative, and the most common notations that we will be using are called the prime notation. So this would be f prime of x or y prime, and the other is called Leibniz notation. And this would be dy over dx, or d over dx, f of x. So these all denote the derivative of f. Now the symbols d and d over dx are called differentiation operators because they indicate the operation of differentiation, which is the process of calculating a derivative. So let's have a look at some examples of calculating the derivative as a function. So here we have f of t equals 5t minus 9t squared. And we want to use the definition of the derivative to calculate f prime of t. So if we use the definition, this is the limit as h goes to 0 of f of t plus h minus f of t, all divided by h. So what we need is to calculate f of t plus h. So this is f times t plus h minus 9 times t plus h squared. So now let's simplify. We have 5t plus 5h minus 9, and we need to FOIL the t plus h and t plus h term. So this is 5t plus 5h minus minus 9 times t squared plus 2th plus h squared. So now if we distribute the -9 through the brackets, we get 5t plus 5h minus 9t squared minus 18th minus 9h squared. So now we can calculate our limit. So we have the limit as h goes to 0 of 5t plus 5h minus 9t squared minus 18th minus 9h squared. And then we subtract f of t, which is 5t minus 9t squared, and that's all divided by h. So we have the limit as h goes to 0 of 5t plus 5h minus 9t squared minus 18th minus 9h squared. And then distributing the negative, we get negative 5t plus 9t squared. And that's all divided by h. And now let's simplify the numerator. We have positive 5t and negative 5t. We have negative 9t squared and positive 9t squared. So we have the limit as h goes to 0 of 5h minus 18th minus 9h squared all over h. We can take out a common factor of h from the numerator, which leaves us with 5 minus 18t minus 9h, all divided by h. Canceling the factors of h's, we end up with the limit as h goes to 0, 5 minus 18t minus 9h. And if we take the limit by letting h go to 0, we get 5 minus 18t minus 9 times 0, which is 5 minus 18t. So the derivative of our function is given as 5 minus 18t. So now that we have defined our derivative as a function, we can now use this to calculate the derivative of the function at a point quite more easily than using our limit calculations. So for example, if I want the slope of the tangent line at 0, then if we substitute 0 into our derivative function, we get 5 minus 18 times 0, which is 5. And if I wanted to find f prime at 1, so the slope of the tangent line where the t-coordinate is 1, we get 5 minus 18 times 1, which is negative 13. And so the derivative function f prime of t can allow us to calculate the slopes of the tangent lines at any point that we wish. So let's have a look at another example. So g of x is the square root of 9 minus x. And we want to calculate the derivative g prime of x. So by the definition, it's the limit as h goes to 0 of g of x plus h minus g of x, all divided by h. So what we need is to find g of x plus h, which is the square root of 9 minus x plus h. And we can simplify by distributing the negative through the brackets. This is 9 minus x minus h. So now we can calculate the limit. So we have the limit as h goes to 0 of the square root of 9 minus x minus h minus g of x, which is the square root of 9 minus x, all divided by h. And so now to calculate this limit, we will want to use the conjugate since we're dealing with square roots. So we're going to multiply the numerator and denominator by the conjugate of 9 minus x minus h minus the root of 9 minus x. And so the conjugate is going to be the same values. So we have the root of 9 minus x minus h, but we change the sign in between the square roots. So now we add the root of 9 minus x. So we multiply both numerator and denominator by this conjugate. And now we FOIL the numerator. So the root of 9 minus x minus h times itself will get rid of the square root. So we have 9 minus x minus h. We have plus root 9 minus x minus h times the root of 9 minus x. We have the minus of root 9 minus x times root 9 minus x minus h. In the last terms, we have negative bracket 9 minus x. And that's all divided by h times the root of 9 minus x minus h plus the root of 9 minus x. So now let's simplify. We have plus root 9 minus x minus h times root 9 minus x, and a minus root 9 minus x times root 9 minus x minus h. So these two terms can cancel. Let us look at distributing the negative through the last brackets. So we have the limit as h goes to 0 of 9 minus x minus h. We have a negative 9 plus x. That's all divided by h times root 9 minus x minus h plus root 9 minus x. Now let's simplify further. We have positive 9 and negative 9. We have negative x and positive x. So we are left with a negative h in the numerator. And that's all divided by h root 9 minus x minus h plus root 9 minus x. And now we can cancel the factors of h. So we have the limit as h goes to 0 of negative 1 over root 9 minus x minus h plus root 9 minus x. And now we can take the limit. So we will let h go to 0. We have negative 1 over root of 9 minus x plus the root of 9 minus x. So this will be negative 1 over 2 times root 9 minus x. So that is our derivative g prime of x. So next we have a few definitions. So we say that a function f is differentiable at a if f prime of a exists. And it is differentiable on an open interval from a to b if it is differentiable at every number in that interval. And so the derivative exists for all numbers between a and b. Now the theorem tells us that if f is differentiable at a, then f is continuous at a. So differentiability implies continuity of the function. However, the converse is not true. If a function is continuous at a point a, then this does not guarantee that the function will be differentiable at that point. So continuity does not necessarily imply differentiability. Now we can also look at finding higher order derivatives. So if f is a differentiable function, then its derivative f prime is also a function. And so f prime may have a derivative of its own. And we can denote this by f double prime or f prime prime. This new function, f double prime, is called the second derivative of f because it is the derivative of the derivative of f. And so here we have some notations to denote the derivatives of higher order. So for the second derivative, we have y double prime. And in Leibniz notation, this would be d over dx of dy over dx. And so it's the derivative of the first derivative. And we can compact this by using this notation. It would be d squared y over dx squared. So this will denote the second derivative of f. For the third derivative, we can use y triple prime, or in Leibniz notation, this would be d over dx of the second derivative, or more compactly, this would be d cubed y over dx cubed. And for any higher derivatives, we would use a number instead of using the number of ticks. So if we wanted to denote the nth derivative, we would use y in brackets the number, f in brackets the number, and in Leibniz notation this would be dny over dxn. So let's have a look at an example for finding a higher order derivative. So let's find the second derivative of the function 1 over x, or the reciprocal function. So in order to find the second derivative, we first need to find the first derivative. So let's find f prime of x. So by definition, this is the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. So we need to determine f of x plus h, which is 1 over x plus h. And so if we substitute this into our limit, we get 1 over x plus h minus f of x, which is 1 over x, all divided by h. So now let's simplify the numerator. We have two fractions, so we need to look for a common denominator. And the common denominator is x times x plus h. So we need to multiply the first fraction by x over x. So we have x over x times x plus h. And then we need to multiply the second fraction by x plus h over x plus h. And this is all over h. And now that we have a common denominator, we can combine the fractions. So we have x minus x plus h, all divided by x times x plus h, and this is all over h. And instead of working with multiple fractions, let's simplify it so that we're only working with one by multiplying the reciprocal of the bottom fraction. So as we're doing this, let's also simplify. We can distribute the negative through the brackets in the numerator. So we have x minus h. This is all over x times x plus h. And we multiply this by the reciprocal of h over 1, which is 1 over h. So we have the limit as h goes to 0. The x and the negative x can cancel. We are left with a negative h in the numerator. And in the denominator, we have x times x plus h times h. And now we can simplify the h's. So this can cancel. And so we are left with the limit as h goes to 0 of negative 1 over x times x plus h. And if we take the limit by letting h go to 0, we have negative 1 over x times x plus 0, which can simplify to negative 1 over x squared. And so this is our first derivative. So now to find the second derivative, we want to find the derivative of the first derivative. And so by definition, this is the limit as h goes to 0 of f prime of x plus h minus f prime of x, all divided by h. And so what we need is to calculate f prime of x plus h. So we know that f prime of x is negative 1 over x squared. So f prime of x plus h is negative 1 over x plus h squared. So now we can calculate the limit. So we have the limit as h goes to 0 of negative 1 over x plus h squared minus f of x, which is negative 1 over x squared. And this is all divided by h. So now let's simplify. We can write this as the limit as h goes to 0 of negative 1 over x plus h squared. We have a double negative, which will change this to a plus 1 over x squared. And this is all divided by h. So now we look for a common denominator for the two fractions. So we have x squared times x plus h squared. So we multiply the first fraction by x squared. So we have negative x squared over x squared times x plus h squared. And we multiply the second fraction by x plus h squared all over x plus h squared. And this is all divided by h. So now that they have the same denominator, we can combine the fractions. So we have the limit as h goes to 0 of negative x squared plus we have x plus h all squared. So we need to expand this term. This is all divided by x squared times x plus h squared. And this is all divided by h. So now let's rewrite it as a single fraction by multiplying by the reciprocal of the denominator. So we have the limit as h goes to 0. we have negative x squared. Now we need to FOIL the brackets. So we have plus x squared plus 2xh plus h squared. This is all over x squared times x plus h squared. And we are going to multiply by the reciprocal of h over 1, which is 1 over h. So we have the limit as h goes to 0. Now let's simplify. We have negative x squared and positive x squared. And we are left with a 2xh plus h squared all over x squared times x plus h squared times h. And now we can simplify. We can factor an h from the numerator, and we're left with a 2x plus h all over x squared times x plus h squared times h. And now the h's can cancel. So we have the limit as h goes to 0 of 2x plus h over x squared times x plus h squared. And if we take the limit by letting x go to 0, we get 2x plus 0 over x squared times x plus 0 squared. So that is 2x over x to the 4, which can be simplified to 2 over x cubed. So for the reciprocal function, f of x is 1 over x. The first derivative is negative 1 over x squared. And the second derivative we found to be 2 over x cubed. So now, is there some sort of pattern between our function f of x, the first derivative, and the second derivative? So you may have noticed that the limit calculations for finding derivatives is quite tedious. And so the next chapter will focus on rules that will allow us to calculate the derivatives of functions a lot easier. So if you can spot a pattern for the different derivatives that we calculated for these types of functions, then this might give you an idea of what we can expect in the next chapter.